All right, now as for standard deviation, we have a population standard deviation. And the population standard deviation is Greek letter sigma. Now that's the lowercase sigma. It's not an O. It's sort of an O with a little curly Q on it. It's the lowercase Greek letter sigma. And again, this is the population standard deviation, which would be calculated on a full census of a population. All right. Actually, in the IQ test, you would consider the standard deviation of 15 to be a sigma, because this is very well established over many, many, many years. So that's considered a population number. But it's rare to encounter a population standard deviation. All right, now letter S, which we've used before, is the sample standard deviation. And these, for samples, or subsets of populations, these are calculated differently, as a matter of fact. And using one calculation, we have sigma, well, sigma squared, the population variance, would be calculated as n capital sigma x squared minus sigma of x quantity squared divided by n. And for the sample variance, s squared, as we've seen, this is n sigma x squared minus sigma x quantity squared divided by n times n minus 1. I've got a little error here. This is n squared. Sorry about that. N sigma, or n squared, and this is over n times n minus 1. So we have changed one of these n's to an n minus 1 when we go to the sample standard deviation. This is a smaller number than, this is smaller than n squared. Smaller denominator means a larger variance, or larger sample standard deviation than the population sample standard deviation. Now, you'll find both on your calculator. And so I have to go to menu to find it on my graphing calculator. But if you have an ordinary scientific calculator, you'll find a button, maybe one looks like this. You might find a sigma n minus 1 and a sigma n button. This would be a population standard deviation. This would be a sample standard deviation. So actually this one on a calculator means S instead of sigma. But anyway, that's, you find those on statistical ready calculators. They use those. And I think on my graphing calculator it just uses S rather than sigma. Alright, so why is there a little difference there? Well, it's I can give this as an example, and I've actually verified this with a very small population sample. There are two ways to sample things. And suppose I have a deck of cards. I shuffle this deck, and I hand you a card. I deal you a card. You look at it, and you give it back to me. I shuffle the deck, and I deal you a second card, and you look at it. Now, when you got your first card, you looked at it, you put it back in the deck, I shuffled, you got another card. Is it possible for you to get that same card twice? Yes, it is. That's called sampling with replacement. You replaced it in the deck, gave it back. So when you sample with replacement, it's possible to get the same measurement again. In this case, not very likely, but it could happen. 1 chance out of 52. All right, now, if I were to shuffle the deck instead and deal 2 cards, then we have done sampling without replacement. And without replacement, it's not possible to get the same card twice. All right, in that case, so the same sample won't show up twice. Well, in practice, when we sample things, we sample, our samples, we don't repeat. We sample without replacement. Well, it turns out when you take a bunch of data and you factor in all these possibilities and take the average standard deviations, the sampling without replacement requires this calculation. Sampling with replacement actually works with this calculation. And so you don't really need to know what I just told you about all that sampling, but in case you have a curiosity about this, why are these different? That's about the best way I can think of to explain that right now. So anyway, there is a small difference in these calculations. These numbers are slightly higher than the population, and it sort of intuitively makes sense that there's a little more chance for error when you sample from a subset of a population. And so you need a little larger standard deviation. All right. Anyway, some food for thought. It's not very critical that you understand that difference. And in fact, I won't be using this calculation at all. So we'll stick with our sample standard deviation. And very rarely will we see a population standard deviation used. Okay, so we'll see other instances where there are Greek letters versus English letters representing population versus sample. We'll see other examples of that show up in the course. All right, now, what's next? The z-score that we calculated, the standard score, actually we don't worry about that so much. What we're really interested in is the standard error of the mean. So let me get that up on the board. The standard error of the mean. And my symbol for this is S with a subscript of x bar. S x bar. Now, your textbook decided to get funny about this, and they call it sex. They have S period E period parentheses x. That's the standard error of the mean. And I think they have x bar there. Anyway, so you'll find that in your textbook. Okay, so after a giggle, this to me is just too much writing. I like to use S x bar, so this is what I will use to indicate standard error of the mean. The standard error of mean is simply the standard deviation, S, divided by the square root of the sample size, the square root of n, square root of sample size. All right, and so now the book gives a definition here which I think is very misleading, and so I want to talk about that. I think they were careless. They're not. You know, if you read everything real carefully, the book, of course, is accurate, but I think the way they stated it was pretty careless. So let me find that definition. It'll take me a second here. Let's see, we're in chapter 4, aren't we? Okay. So